Today we shall discuss about mathematical expectation 2. 2 means here we shall consider two random variables. We have already known about how to calculate expectation for one single variable, expectation of x, and we denote it by small m. Here we are considering, suppose, two random variables x and y, and let g be a function from r cross r to r. It's a continuous function. Then how to calculate expectation of, suppose, g of x comma y, a function using two random variables x and y. Then here two cases can arise. X and y both are discrete and both are continuous. Now for the discrete case, the value of expectation of gxy will be summation over I, summation over j, g of xi comma yj, f of ij. What is f of ij? F of ij means the probability at I comma jth point. And if it's a continuous case, then expectation of the same quantity will be integration minus infinity to infinity, then integration, again integration minus infinity to infinity, g of x comma y into f of x comma y dx dy, where what is fxy? It is the probability density function. Okay, so for two variables, this is how we calculate the expectations, where g is any continuous function. Now suppose this gxy becomes a single function of x, that is there is no y. In that case, the expectation for continuous case, it will become minus infinity to infinity, then minus infinity to infinity, g of xy, that will become g1x into fxy dx dy. Again we know, if we write it like this, putting that g1x over here, then minus infinity to infinity fxy dy, then writing dx. Okay, now check this quantity. This gives the marginal distribution of x, that is minus infinity to infinity g1x fxx dx. So if that function gxy, instead of taking two variables, it becomes only single variable function, then the expectation reduces to this, what we have already learned. Similarly, if it reduces to only single function, say suppose g2y, using single variable y, then it will look like g2y fyy dy. Okay. Now we have few properties of that joint distribution. Property number 1, that is expectation of g1x comma y plus g2x comma y plus dot dot up to gn x comma y is equals to expectation of g1xy plus expectation of g2xy plus dot dot expectation of gn x comma y. That means we can divide their expectations. Proof is very easy. You take any of the variables, either discrete or random variables. Suppose I am taking the discrete one first. Then what we can write for that line? It will give you summation over I, summation over j, then g1 x comma y xi yj plus g2 xi yj plus dot dot gn xi yj, that whole thing into bracket into the probability function, which is f of ij. Now separate all that summation. So summation over I, summation over j, g1 fij plus summation over I, summation over j, g2 fij plus dot dot the nth term. Okay, now this gives you expectation of g1 x comma y. This gives you expectation of g2 x comma y, and so on. Okay, so this proves property number 1. Next we have property number 2, which is expectation of k into gx comma y equals k expectation of gx comma y. Proof is very easy like the previous one, so I am skipping it. That means you can put that k outside of that expectation. Okay, number 3 property is very important for exam, which is expectation of g1x comma g2x equals expectation of g1x into expectation of g2x if, so g2y, if x and y are independent random variables. If x and y are independent random variables, otherwise not. Okay, so if x and y are independent random variables, we can write down expectation of g1x into g2x equals expectation of g1x into expectation of g2x. So let's prove it. Here we will also take two cases, either discrete or continuous. So I have proved the last one as taking discrete case. Now proving this one by taking continuous case. Proof is very easy. So if these are continuous, what will be this value? Expectation of g1x into expectation of g2y. That one will be minus infinity to infinity, then minus infinity to infinity. This function g1x, g2y, fxy, dx, dy. Right? Now both expectation of g2x and expectation of g2y both are exists. So we are starting with this thing, minus infinity to infinity g1x minus infinity to infinity double integration g1x f of x comma y dx dy. Okay, just like the previous manner, we can write it like this, keeping that g1x first, then minus infinity to infinity fxy dy, then putting dx. This quantity becomes our fxx, so minus infinity to infinity g1x fxx dx. Okay, again we can write similarly for this integration, minus infinity to infinity g2y f of xy dx dy. For this we can write by approaching similarly, minus infinity to infinity g2y f yy dy. Right? Now it is given that x and y both are independent random variables. So for independent random variables, we know the probability density function can be written as this, that is joint density function equals to the product of the marginal density function. Okay, then starting with expectation of g1x, g2y, it already we checked that it has the formula minus infinity to infinity this g1x, g2y, fxx, fyy dx dy. Instead of f of x comma y, in the value of expectation of g1x, g2y, we are putting this range because we can write that because x and y are independent random variables. Now you write it like this. This is by the property of double integration. We can do that because all are single variable functions. g2y fyy dy. So the first quantity is expectation of g1x and the second integration is expectation of g2y. Okay, this proves the property. Next property is property number 4, that if g of xy greater or equal to 0, then expectation of g of xy will also become greater or equal to 0 if they exist. Okay, not necessarily always expectation exists, because it is depending on the absolute convergence of either the series for discrete case or for the improper integral for the continuous case. So if this happens, if the expectation exists, then if the function is greater or equal to 0, the expectation value will also become greater or equal to 0. Now next thing is moments. We have already checked moments for single variable, as a single independent, single random variable. Now here we are considering two random variables x and y. So moment is denoted by, we say it r plus kth moment, r plus kth moment about origin, and we denote it by alpha rk, and it has the value expectation of x to the power r, y to the power k. Okay, so this quantity is known as r plus kth order moment about origin, and it is denoted by alpha r comma k. Now clearly by putting different values of r comma k, you will get the value of that moment. So if you put both at 0, that is alpha 0 0, that means expectation of x to the power 0, which is 1, into y to the power 0, which is again 1. So expectation of 1 is 1. Next alpha 0 1, that is expectation of x to the power 0, which is 1, into y to the power 1, that is expectation of y. We can denote it m in suffix y. Similarly alpha 1 0 will be m x, and so on. Okay, now next thing is, if you take that this quantity expectation of x minus mx whole to the power r into y minus my whole to the power k, this is known as bivariate central moment of order r plus k, that is r plus kth bivariate central moment. Central moment because we are taking it with respect to the center, that is the corresponding means mx and my. Okay, and it is denoted by mu rk, mu rk. So similarly we can find the value of different values for r and k. So mu 0 0 is 1 0 0, that means expectation of 1, which is 1. Next mu 1 0, that will give you expectation of x minus mx. Similarly mu 0 1 will also give you some value. Mu 1 1 will give you expectation of x minus mx into y minus my. Okay, these are called central moment. Now if the variances of corresponding x is known as sigma x square, and variance is known as sigma x, that is the standard deviation. Say standard deviations are taken as sigma x square for x, and for y if we take it as sigma y square, that is variance of x are sigma x its whole square, and variance of y is sigma y its square. If we name it as this, then check mu 2 0. If you consider it, what you are getting, expectation of x minus mx its whole square. Clearly this is the variance of x, which is known as sigma x square, or the square of standard deviation. Similarly mu 0 2 is also sigma y its whole square. Okay, so from here we are getting a new quantity which is called covariance, and quite important also, covariance of x and y, which has the rule that is expectation of x minus mx into y minus my. Okay, so we are considering this whole quantity, that is the value of mu11 as the covariance of x and y. Now next from the covariance we are defining another thing which is called correlation coefficient. Correlation coefficient, and which is denoted by rho x comma y, and it has the value that covariance of x comma y by sigma x sigma y. This is also another important thing, that is rho x comma y equals covariance of x comma y by sigma x into sigma y. Okay, now let's solve one example, that is how to calculate the covariance or the value of rho. So let's take one discrete example for discrete case. Now the example says that two balls are drawn without replacement from a basket having three balls numbered 1, 2, 3. Let x be the random variable denoting the number on the first ball, and y be the random variable denoting the larger of the two numbers drawn. Okay. Then find covariance of x comma y. So two balls are drawn without replacement, that is we are drawing the first ball, then we are not replacing it, again drawing another ball from a basket which has total 3 balls numbering 1, 2 and 3. So and x denote the random variable, the number on the first ball, and y denote the larger of the two balls. So we have to find the covariance of x and y. So to compute the covariance, first we need the mean. Now to calculate the mean, we need the spectrum and the corresponding probability function, that is the distribution table. So first try to find out the spectrums. What could be the spectrum for x? X is the number on the first ball. So the number on the first ball can be 1, can be 2, can be 3. So spectrum of x is 1, 2, 3, and y is the larger of the two numbers. So if you suppose drawn two balls 1 and 2, larger will be 2. Suppose you have taken two balls 1 and 3, larger will be 3. You have taken two balls 2 and 3, larger will be 3. So it is already here, that means the only possible way of y could be 2 or 3. Okay, now let's find out all the possible probabilities, that is probability of x equals to 1, y equals to 2, x equals to 1, y equals to 3. Similarly, x equals to 2, y equals to 3, and so on. Okay, I'm calculating the first one only. So probability of x equals to 1 and y equals to 2. First we are considering the denominator. That means without any condition imposed, in how many ways can we take two balls from an urn having three balls? So without replacement. Okay, so for the first ball we can take it by three ways, because there are three different balls. So 3 into, check for the second ball, when we are drawing it, there is already one number of ball is decreased, that is they contains only two balls, so we can draw it by only two ways, that is 3 into 2. Now check the denominator, x equals to 1, that means the number on the first ball must be 1. Okay, so it can be done in only one way. Now the number in the larger of the two numbers is 2, that is y equals to 2. So it could be 1, 2, that means first ball is already 1. To become the maximum is 2, the second ball must be 2. So only one possibility arises here, that is 1. So 1 by 6. Similarly, all the probabilities can be calculated. Now next, these are all joint probabilities. Now next we need to consider the marginal probabilities also. That is probability of x equals to 1, probability of x equals to 2, and probability of x equals to 3. Let's find out probability of x equals to 1. So without any condition imposed, denominator will be 6, and think about the numerator. X should be 1, y could be anything. That means the first ball drawn should be the number 1 ball. So this can be done in one ways. So 1 into, think about the second ball. In how many ways can we do that? There are 2 balls left in the basket, so we can take it by 2 ways. So 1 into 2, that means 2 by 6 is 1/3. Similarly, we can calculate this 2 also, and for y also, probability of y equals to 2, probability of y equals to 3 also. Okay, now make the table for x, 1, 2, 3 spectrum points. Write down the corresponding probabilities. We have already calculated for probability of x equals to 1, which is 1/3. Similarly, put the other values also. Then make the table for y, 2, 3, put the values and compute all that expectation of x, expectation of y, expectation of xy, and so on. Then calculate the value of covariance of xy. Okay. Now here we have few properties of covariance and the correlation function. So the first property here is number 1, covariance of x comma y equals to expectation of xy minus mx my. Let's prove it. Proof is very easy. What is the definition of covariance of xy? That was expectation of x minus mx into y minus my. So expectation of, opening the bracket, xy minus mxy minus x mx minus minus plus mx my. Open the bracket, expectation of xy minus mx is a constant, so putting it as it is, mx into expectation of y minus expectation of x into mx plus mx my is again a constant, keeping it as it is. Now check, this is our my, so in the next line we can write it minus mx my minus, this is also our mx. Okay, that one will be my. So mx my plus mx my, 1 mx my plus minus got cancelled out. So we got the result, this one, for covariance of xy. Okay, so to calculate covariance of x comma y, we generally use this formula. This is way much easier to calculate. Okay, next property is property number 2, rho of, that is correlation coefficient, ax plus b comma cy plus d equals ac by mod a into mod c into rho x comma y. Okay, let's calculate it. Here this is one variable, here it is another variable. So first we are considering the expectation of these two variables. Expectation of ax plus b, that will become a into expectation of x plus b, that is a mx plus b. Similarly, expectation of cy plus d, that will be c my plus d, right? Now starting with covariance of these two variables, x plus b comma cy plus d. According to the formula of covariance, that will give you expectation of this variable, that was x minus mx. So this variable minus its mean. So ax plus b minus amx plus b into we need to put it another bracket into cy plus d minus cmy plus d. Okay, opening it, plus b minus b got cancelled out, a into x minus mx, then c into y minus my. Putting that a and c are constant, keeping it outside, expectation of x minus mx into y minus my, that is ac into this thing gives you covariance of x comma y. Okay, now we need, for the value of rho, we also need to consider the standard deviations. So let variance of ax plus b, according to the rule we have the formula a square equals to variance of x, which is a square sigma x square. Similarly, variance of cy plus d will give you c square sigma y square, right? Now starting with rho of ax plus b comma cy plus d, according to the formula, it has the formula covariance of this whole quantity x plus b comma cy plus d by their sigma x and sigma y. That means by a square, not a square, it's square root, that is a sigma x into c sigma y, right? Now this thing, now a and c could be negative also, so we need to take mod over it, but sigma x sigma y both are always positive because they are positive square root of variance, so no need to take mod over them. And this thing is, we already calculated ac covariance of x comma y by mod a mod c sigma x sigma y. Now this whole quantity is rho xy, so we can write it ac by mod a mod c rho x comma y. This proves the result. Next one, another very important property, that is -1 less or equal to rho x comma y less or equals to 1. Okay, that is the value of the correlation coefficient always lies between -1 to 1. To prove it, we are taking a function g of x comma y equals to this x minus mx by sigma x plus y minus my by sigma y. Okay, now x minus mx by sigma x plus y minus my by sigma y, its whole square, it is greater or equal to 0. Okay, so its expectation will also become greater or equal to 0. We just checked from a property. Now open it. Expectation of x minus mx by sigma x its whole square plus expectation of y minus my by sigma y its whole square plus 2ab, that is 2 into expectation of x minus mx by sigma x into y minus my by sigma y. This whole quantity is greater or equal to 0. Now check this thing. This is a constant. We can put it outside of the expectation. So this gives you 1 by sigma x square expectation of x minus mx its whole square. Similarly, from the second term, 1 by sigma y square expectation of y minus my its whole square plus 2 into 1 by sigma x sigma y expectation of x minus mx into y minus my. Whole quantity is greater or equal to 0. Now this thing is our variance, so sigma x square by sigma x square. Similarly, this is also variance, sigma y square by sigma y square plus 2 into, this is our covariance by sigma x sigma y, so that gives you rho. So rho xy greater or equal to 0. This is 1 plus 1 2, taking common 2, so 1 plus rho xy is greater or equal to 0. Similarly, that means rho xy is greater or equal to -1. Similarly, we can prove this is also less or equal to 1. Next topic is uncorrelated random variable. Now when two random variables are said to be uncorrelated if their covariance value is equals to 0. Okay. Now clearly this implies that is when they are uncorrelated. Obviously when covariance 0, rho xy will also become 0. Now we have another theorem, that is if x and y are independent, then rho x comma y will be equals to 0. Proof is very easy, I am leaving it for you. So when they are independent, the correlation coefficient value will be equals to 0. Next there is another theorem or some property is also there. Variance of ax plus by equals a square sigma x square plus b square sigma y square plus 2ab covariance of x comma y. Okay, the proof is just like the previous one, where we have proved that rho of ax plus b comma cy plus d, that is property number 2, equals to ac by mod a into mod c rho x comma y, just like that.